Now, our other method of solving uh, equations that we can't solve readily, like with polynomials or anything else, is called Newton's method. Obviously named after Sir Isaac Newton. Well, I would assume so. It's not Bert Newton, obviously. So, what we're looking at this time is the idea of we've got a curve here and we take a tangent to a curve. Now, if you notice at x1 here, we've taken a tangent to the curve. And when we take that tangent to the curve and find the root of that tangent, we notice it actually gets closer to the root of the polynomial there, or the curve itself. It doesn't have to be a polynomial, it can be any function there, but it gets close to the root of that function. So again, if we take the tangent, we take the value of the tangent there at x2 and get a new tangent at that point, notice again it gets closer. Again, if we took the tangent at x3 there, it would get closer again, and so on and so on. So we would assume that if we keep doing this, we're going to get the root of the tangent is going to get closer and closer and closer to the root of the polynomial again, or the function, and we're going to depend on what accuracy we want for that and how many times we want to do it. So that's what we do. Take x1 is close to the root. Now it should be close to the root there, and we said it works on the idea that we can get an equation of the tangent. So at x1, we get the point there, x1, and the y1 would be the function of x1, obviously, when we plug it into the curve, and the gradient of the curve would be the derivative at x1, so the derivative of the function at x1. So when we rearrange this and put in the new values here, when x is equal to x2, that's where the new tangent crosses the x-axis, and obviously because it crosses the y-axis, y would be 0. We sub those values in, and then if we rearrange all this, we have the minus function of x1 divide by the derivative of the function, and then add x1, we get x2 by itself, and the new value here would be the old value x1 minus the derivative function of x1 over the derivative of x1. And there's your formula for Newton's method. So that's how we're going to do it. So any new value we want to get using Newton's method relies on taking the old function value, the old x value, minus the function of the old value over the derivative of the old value. So if x1's close to the root, and from our graph we know that x2 would be closer, x3 would be even closer when we apply Newton's method to it again. So again, keep repeating this process and you would get closer and closer to that root, because the accuracy starts to get more decimal places. So that's what we're looking at with Newton's method. So let's look at applying this. So taking x is equal to 1.9. Now x point 1.9 into this function, notice there's no degree symbol. We're working in radians, so remember that. Oh, we're moving it around, which is not great. So, but remember, this is in radians. So when we're going to sub it in, make sure your calculator's in the right mode. So it's very important. So we're told x is 1.9 is a close first approximation of this. How much closer can we get with another application? So we need to get the derivative of this function. X on 2 minus sine x becomes a half cos of x. So taking the 1.9 minus the 1.9 on 2, because we sub it into the function, minus sine of 1.9, all over the derivative of the function. When x is equal to 1.9, we get a half minus cos of 1.9. Throw it in your calculator. There's your second approximation, correct to 4 significant figures. So there's one application of Newton's method. If we wanted to get closer, we'd apply it again. Depends on how many times we want to apply it. So this time we're told take 1.1 as the first approximation. We've got x on 4 minus natural log of x squared, and use Newton's method. So we know that the derivative would be a quarter minus 2 on x, and we're going to get 1.1 minus the 1.1 for x here and the 1.1 for x in there, over a quarter, 0.25, minus 2 on the 1.1. Again, throw that straight in your calculator, get your new approximation 3 decimal places. What we've got to be careful about, some curves, where we want to take them, and we've got to be really careful about our first approximation. Now, When we look at this one, if we take our approximation to x1 and then get the tangent at x1, we notice that the curve's going to fall away from it. It's not great. So probably not a good idea to try and take your function value on the inside of the curve where it's concave down there. Okay, similarly here, you can see that when it was x1, it's starting to move away, so it might not get a great value. It might get closer, but be really careful. So if your second approximation is further away than your first approximation, you haven't picked on the right side of the curve, so be careful. So if we look at 3 here, so on the graph here, we're going to take, we want to find the approximation for the root b. We know it crosses somewhere here, but if we take this value here at a, what we notice when we take the tangent, it's actually getting further away than our first approximation. We need to be somewhere on this side of the turning point to take our approximation to try and play with it. So just be really careful there. That you're choosing a point that's actually going to work. So that could be that's the problems we get with Newton's method. So show that we get this function here has a root between 0 and 1. Well, we know how to do that. We sub in 0, we sub in 1. We see that there's a difference in sign. So if there's a difference in sign for our y values, it means that a 0 or a root must lie between those two. So if we look at this one, can you use Newton's method with the first approximation of x is equal to a quarter to this root? So if we sub it in, we get the derivative, and that's what we need to do. We need to get the derivative, and we sub function of 0.25 into Newton's method into the derivative here. We get 0, which is going to be a problem, because if you remember, if you think about what the formula for Newton's method is, it's x2 equals x1 minus the function of x1 over the derivative of the function of x1. So if we look at that, getting 0 is going to give us an error here. Why is it an error? Well, when we get a first derivative equal to 0, we know that the curve's stationary. So it's saying at a 0.25 or a quarter here, then we're getting the curve turning. Now if you take tangent, and this is what Newton's method is based on, tangents at turning points are horizontal. It's not going to touch the x-axis. That's why it's a problem. So you can't. There's another problem with Newton's method. Don't take your first approximation on a turning point. It's not going to get you it's not going to get you a tangent that's going to cross the x-axis. So that's why it's going to be an error. So keep that in mind. If you get this situation where it's 0, realize that's why you're not getting something for Newton's method. It's failing for you there. So 0.7 would be a better approximation, because it gives us a value when we substitute it into 0.7 there, and we've got the function of 0.7 over the derivative of 0.7 gives us 0.753. Not a bad first approximation. Our second one's it's pretty good. We find the exact value of the root. Well, we can factorize. It's only a quadratic. So this root would be giving to us by 3/4. There's actually 2 roots, but the one we're looking for here is 3/4. Okay, well, 0.753, it was getting pretty close. 0.753, it's getting pretty close there. So not bad, not a bad effort. Let's have a look at question 5 there. So we're going to compare two methods this time. So we've got the function. We show that we've got a root between -1 and 0. That's pretty cool. And then we want to halve the interval. So to get and show the root lies between -0.25 and 0.125. Well, we know it lies between -1 and 0. So let's take -0.5. We get it negative. So we've limited our interval between -0.5 and 0. We sub in 0.25, halfway between the previous interval. We get that it's negative, so the root now lies between 0.25 and 0. Halve it again, and then we get 0.125, which is greater than 0, which means our root lies between 0.25 and 0.125. So there's our interval that we wanted to find. And then, well, let's use Newton's method, and 0.25 as a function to start off with. get a better second approximation? Well, our derivative of our function is there. We substitute our values in to the function, the derivative of the function. Again, put it all straight into the calculator. They'll do it nicely. And gives us minus 0.0197. So we can see there that that works very nicely to get a root that's pretty close. This type of question here is a little bit tricky with this one. Cube root of 30. We want to find it at 3 decimal places, and we want to use Newton's method. And it's always a tricky one for students. Like, until you say, well, if we're going to find the value, then we'll let x be equal to the cube root of 30. Or that could be coming to the x cubed minus 30 is equal to 0. Well, there's our function that we can try. If we graph that up, that's actually going to cross the x-axis. So where does it cross the x-axis? Well, we want it told it's going to be close to 3. So use Newton's method. Derive that function, 3x squared, and use the value of 3 to sub it into the function, and the derivative of the function gives us 3.111, which is a approximation of cube root of 30 to 3 decimal places. So that's how we do that type of question. You'll see that one come up sometimes. That's how we do it. So question 7, here's our function, and told it's got a root near, we'll show it has a root near 1. So we take 0.5, we take 1, we see a change in sign. We just need to get close to 1 and get a change in sign somewhere close to it. Well, it's within an interval of a half. That's pretty close. Take 1 as our first approximation. Use Newton's method again, so get our derivative. 1 minus the derivative there. Why does the attempt fail? Oops, that gave us an error. So obviously that was 0, and when we subbed it in, our calculator went, sorry, can't do that. So what's the problem? Turning point. If I get an error from there, it must be a turning point. So I've just got to be careful and realize if I do get an error there, it's going to be a turning point, and so I won't be able to use 1. I'd have to use something. Try, if you're going to do it, use 0.9. That's probably going to be a little bit better.